This is a lecture over the rational root theorem for Math 107, Chapter 3. In the previous lecture, Descartes' rule of sign gave us the number of positive roots, or the different possibilities of numbers of positive roots, negative roots, and complex conjugate pairs for the roots of a polynomial, but it gave us no numbers. Rational root theorem will give us actual values to try out. And this is how it works. Again, this is presented here with no proof. If I have a polynomial in x, then I will have some kind of leading term. Let's say this is 25 x to the 9th minus, doesn't matter what's inside here, and then we'll have a constant. Let's let that be 6. Alright, the rational root theorem says that every, or all, whichever way you want to look at it, rational root is equal to a fraction made out of the factors of the constant, in this case 6, one of the factors of 6 divided by one of the factors of 25. What is a rational number? A rational number is a number that can be written as the fraction, as the ratio of two integers. Example, 3 over 2. That's a rational number. 3 is an integer, 2 is an integer. Minus 1 over 12. That's another rational number. Numbers that can't be expressed as rational numbers are called irrational. Some of them have names. The two famous ones are pi and Euler's number e. Also, the square root of 2 is an irrational number. The square root of 3 is an irrational number. Sometimes we look at the decimal expansion and say it never repeats and never terminates to say that it's an irrational number, and that's one way to look at it. But also, you can say that it cannot be expressed as the ratio, as the fraction of two integers. So this is why it's called rational, because I'm taking the integers associated with 6 with the constant term and divided them by some of the factors associated with 25. It seems like a very artificial construct, but you will get a list out of this, and these list of numbers can be tried in the polynomial. There's two ways to try them out, and you can find the rational roots this way. Of course, you don't want these coefficients that you're finding the factors for to be something too complex, so you better use a computer. For example, if it was 60 or 120, think of how many factors there are of 60, or 12. In fact, you end up with quite a few possibilities very rapidly. So here's this polynomial, which isn't too bad. 2x cubed plus 3x squared minus 8x plus 3. So the rational root theorem says I should take the factors of the 3 and divide them by factors of 2. And you have to see this, it's hard to say in words. So for the 3, what are the factors of 3? Just make a list of them. Well, basically it's 3 and 1. That's the only two numbers that you can multiply together and get 3. But they could be negative. So you could have minus 1, minus 3, 3, and 1. Now when you make this list, it does not imply, it's not like a factor tree where you're implying that minus 1 times minus 3 times 3 times 1 equals 3. No, instead you just list all the factors as though just some kind of numbers. You write them down. Now for 2, you do the same thing. This is a pretty easy example. So you have minus 2, minus 1, minus 2, and 2 and 1. Then you take these two numbers, these two sets, and you make all these fractions. And that gives you all the possibilities. Of course, it takes, it goes pretty fast. Okay, this is in the numerator, and these are in the denominator. Here's what they're going to look like. Minus 1 over minus 1. Then I could have a minus 3 over minus 1, a 3 over 1, and a 1 over minus 1. This is going to take some time and a lot of paper. Right? Then I keep going. Now minus 3 over minus 1, minus 3 over minus 2, minus 3 over 2, and 3 over 1. I'm just going to write this out for your benefit so you don't have to see it again. 3 over minus 1, 3 over minus 2, 3 over 2, and 3 over 1. And now I'm looking at this last number here. I've got 1 over negative 1, 1 over negative 2, 1 over 2, and 1 over 1. Now, because of these negative and positive signs, things cancel, so you end up with a smaller set to try. So now we'll look through here. Well, negative 1 over negative 1 is the same as 1 over 1, so I'll just forget this and use this one. Minus 3 over 1 is the same as 3 over 1, right? Because the signs are canceled, so I'll cross that off the list, which is actually the same as this. And now I have a negative 1, which also occurs here. 3 over negative 1. Somehow I think, no, that's how it would work out. Alright, so get rid of this one. Minus 3 over minus 1 is the same as 3 over 1, so I can forget that. This would be 3 over 3 halves, which is also here. So just go through the list and prune it. And here's a minus 3 halves. Don't need this one. And a minus 3, and a 1, and a 3, and negative 1, and a 1. The 1 halves stay. So that gives me a smaller list. So let me write that smaller list on the next slide. So here are the numbers that stayed. Minus 3, minus 3 halves, minus 1, negative 1 half, a 1 half, a 1, 3 halves, and 3. So that gives me 8 possible rational roots. Any root of that polynomial that's rational will be one of these numbers. So how do you check the numbers out? You could do it two ways. You could take your original polynomial and you could try to divide it. For example, if I want to test out 3, I could go x minus 3 and see what I get. If the remainder is 0, then this is a root. The other way to do it is to take the 3 and put it in the polynomial. If the answer comes out to be 0, then the 3 is a root. So you have two ways to check it. Here's one way, and here's the second way. And if you couple this with Descartes' rule of signs, then say you were supposed to find, you had a maximum number of one negative root. Then if one of these numbers, one of the negative numbers, turns out to be a root, you don't have to look at any of the rest of the numbers. You can use that to do more elimination of the work that you have to do. For this particular function, I did work out Descartes' rule of signs in the notes. So here's a p of x equals 2x cubed plus 3x squared minus 8x plus 3. And when I look for the sign changes here, doesn't count. This counts as 1. This counts as 1. So 2 is the max for the positive roots. Then I go back and put the negative x in here. I have 2, and I have a minus x cubed plus 3 times minus x squared minus 8 times a negative x. Remember to use parentheses. Working out the algebra, this would be minus 2x cubed plus 3x squared plus 8x plus 3. Sign changes, there's only one of them. So there's one maximum number of negative roots. So here would have been my possibilities here. I need total has to be 3. Here's complex conjugates here. This is a number of negative roots, a number of positive roots. Well, I could have 2 and 1. I don't need any complex numbers, right? The 1 can't change because if I drop the 1 down for the negative roots, it would become minus 1, so it just stays as 1. But the 2 could decrease to 0. If I have 0 and 1, I'd need a complex conjugate pair to get 3. So those are all my possibilities. And now the rational roots, remember the root might not be rational, but if it happens to be rational, then you're done. I'll write these in a list here. So these are the numbers I'm looking at. Plus and minus 3, plus and minus 3 halves, plus and minus 1 half, and this is like working very well. So I will write that on the next piece of paper. Well, maybe I can do it right here. I'm trying to do better. Okay, here were the roots that I had possibilities of. Plus or minus 3, plus or minus 3/2, plus or minus 1, and plus or minus 1/2. At least we have some numbers to try. Now, remember, if one of these roots, this negative root, one of these negative values shows up as a root, then you can stop looking at all the other negative values. Okay, and how do I try this? I take these numbers, the plus and minus 3, the plus and minus 3/2, plus and minus 1, plus and minus 1/2, and one of the easiest ways to do it is substitute it into this equation and see what you get. So I take that original equation, and when I put 1 into it, I would have 3 times 1 cubed plus 3 times 1 squared minus 8 plus 3. Well, that ends up being 8 minus 8, right? It's 0. So x equal 1, or you could say r1 equal 1, is a root. So I found one of the roots, one positive root. Now I could try another number, like say 3/2, and if you work through the algebra of that, you'll find out it's not equal to 0. So you have to keep looking. And I could try the 1/2, and that does equal 0. So here's another root. So I had a maximum of 2 positive roots. They could be rational or irrational, but since I found 2 positive roots, I know I won't find any more positive roots. So the first one is 1. The second one turned out to be 1/2. So now I can go look for the negative root. Remember, it might not be on this list if it's irrational. So I could take that original equation and I could try -1. Remember, we had quite a list there, and so we just start plugging them in. And if you work through this, you will find out that it's not equal to 0, so -1 is not a root. However, if you put -3 into this equation, you get 2 times -3 cubed plus 3 times -3 squared minus 8 times the -3 plus 3. And that does equal 0. So -3 is the negative root. And that's how those two theorems go together. Descartes' rule of signs sort of tells you, it gives you a ballpark idea of how many positive roots, how many negative roots, and how many complex conjugates you can expect. But it doesn't give you any numbers to try. The rational root theorem, by allowing you to construct those fractions based on the factors of the constant term divided by the factors of the leading term, gives you a list of possibilities to try. And you can work those together to sort of simplify your work and see if you can find some roots that way. Now, be very aware that seldom are the roots rational. They're usually irrational. So this is okay, and it's just like as with Descartes' rule of signs, it only goes as far as it goes. But these are two theorems that you can use. So you have to do this on homework. Hopefully you see how to do it now. The next lecture, I'm going to show you a method that is used in computers to find the roots of polynomials.